All right, let's get right into it. We're always hearing about how AI models are getting bigger and more powerful, right? But how do we actually make them small enough to be useful in the real world? Well, today, we're going to demystify quantization. It's this really clever technique that makes these massive AI models practical for, everything from huge data centers all the way down to your smartphone.
Just to give you a sense of the scale we're dealing with, look at this number, 720 gigabytes. That is the insane size of a top-tier open-weights AI model, a model called DeepSeek R1 in its original, high-precision format. I mean, that's bigger than the hard drive on a lot of laptops.
Now, what if I told you we could take that exact same model and shrink it all the way down to this, 131 gigabytes? That is an 80% reduction in size. This right here is the magic of quantization. And frankly, it's what makes it even possible to run these things on the hardware we have today.
So this brings us to what I like to call the gigabyte problem. Our AI models are unbelievably powerful, no doubt, but in their raw form, they're just too big, too slow, and way too power-hungry for any kind of practical, widespread use.
And here's the thing, this isn't just a problem for giant cloud servers. On one end of the spectrum, you've got massive data centers struggling to run these models efficiently. And on the complete other end, you have tiny devices like a smart camera, which has very limited power and definitely can't handle the complex math these models are built on. Quantization is the bridge that solves the problem for both.
So how does this whole thing actually work? Well, at its core, quantization is a brilliantly simple idea. It's basically the process of mapping a huge, continuous range of numbers into a much more limited set of discrete buckets. Think of it like simplifying the language that the model speaks.
This quote just nails the counterintuitive nature of what we're doing here. We are on purpose, strategically throwing away precision. We're making the numbers less accurate to make the whole model more efficient. It sounds completely bonkers, right? But it works.
This slide breaks it down perfectly. So, imagine that top line represents every possible number between 0 and 1, an infinite number of them. Quantization comes in and just splits that line into a fixed number of buckets, say 10 of them. So a specific value like 0.42, boom, it gets mapped to bucket number 4. And any other value that's close, like 0.45 or 0.48, also ends up in bucket number 4. We lose those subtle differences for sure, but we gain this massive simplicity.
Okay, so that brings us to the big question. Why? Why are we going through all this hassle? Why are we so obsessed with forcing these super complex models to use simple integers instead of the high-precision floating point numbers they were built with?
Well, the answer is all about efficiency, and you can see it plain as day in this table. Look at the representation row. Integers are just simple binary numbers, while floats are this complex thing with a sign, an exponent, and a mantissa. And that complexity directly impacts speed. Integer math is lightning fast, usually just 1 clock cycle per operation, versus 3 or 4 for floats. And then you look at size, and the difference is huge. An int, an 8-bit integer, compared to an FP32, a 32-bit float, that's a 4 times reduction in size right off the bat.
So the reason floats are so complicated is because they're made of those 3 separate parts. Just to add 2 of them together requires multiple steps. Integers? Nope, you just add them. That extra complexity is a direct tax on your speed, your memory, and your power consumption.
Okay, so we get the what and the why. Now let's get into the how. Turns out there's a pretty neat mathematical recipe for converting these floats to integers without completely breaking the model.
First things first, we need to know the range of numbers we're actually dealing with. Floating point numbers can represent a nearly infinite range, but the actual weights inside a neural network usually live in a much, much narrower band. So we find the real minimum, let's call it alpha, and the real maximum, beta. This is our clipping range.
Next up, we need a conversion factor. We call it the scale, or just S. It's basically the ratio that maps our big float range down to our tiny little integer range, like figuring out how to represent all the numbers between, say, -1 and 1, using only the 256 possible values of an 8-bit integer.
And finally, we need an anchor to make sure everything lines up. That's the 0 point, or Z. It's a really important offset that makes sure the real value of 0 in the float world lands in the correct integer bucket in our new world. This is especially crucial if our clipping range isn't perfectly symmetrical around 0.
So, you take these 3 ingredients and they all come together in this one pretty straightforward formula. Here's how it works. First, you take your original real value, r, then you divide it by our scale factor, s. Next, you just round that result to the nearest whole number, and finally, you add that 0-point offset z. And that's it. You just converted a float into its quantized integer 20.
But, and this is a really big but, let's not forget the trade-off here. Every single time we do that rounding step, we're losing information. We're losing precision. The entire art and science of quantization is really just finding that perfect sweet spot, losing just enough precision to get those massive efficiency gains, but not so much that the model's performance starts to tank.
So, we've walked through the mechanics. We've been deep in the weeds. Now let's pull back up and talk about the real payoff. How does this clever mathematical trick translate into real-world impact and make AI practical for all of us?
So when does all this happen? Well, you can't actually train a model with these simple integers. You need that high precision of floats to do all the complex math during training. This means quantization almost always happens after the model is fully trained in a step we call post-training quantization, or PTQ. Then that shrunken, super-efficient model is ready for inference, which is when it actually starts doing its job and making predictions. And the payoff here is just huge. You get way smaller models, which means they're easier to store and send around. You get much faster inference, so your apps feel snappier. You use far less power, which is the absolute key to running advanced AI on your phone or in your car. And all of this leads to lower costs, which is what truly makes AI accessible for every person and every business.
And it gets even more sophisticated. It's not a one-size-fits-all kind of deal. You don't have to apply one single rule to the entire model. You can get really granular, applying different quantization strategies to different layers of the model to perfectly fine-tune that balance between performance and precision.
Now, if all this math seems a bit intimidating, the good news is you probably won't have to do it yourself. Major frameworks like PyTorch and TensorFlow have powerful built-in tools that honestly handle most of the heavy lifting for you.
So, think about this journey we've been on. We started with these big, clunky 32-bit floating point numbers. We've managed to shrink them all the way down to 8-bit integers, then 4-bit, and researchers are even pushing the boundaries with 1-bit models now. It leaves us with a really fascinating question for the future. Just how much further can we shrink our models before they finally break? And what incredible new possibilities will that unlock?